You can start. Okay. Well, welcome back to week 8. We're going to do one presentation from a group of students, seniors in chemical engineering, about a heat exchanger experiment. But I thought before we talk about the heat exchanger experiment, let me talk a little bit about, a little bit of background, as it were. So the experiment you're going to hear about from Jonathan Savoy and his group is understanding a coil tube heat exchanger. So it's Jonathan Savoy, Peter Wentz, Brian Call, Bill Urban. So before we discuss heat exchanger, let me discuss the concept of what's called unit operation. What is the unit operation? Distillation is a unit operation, which means that you can combine everything you want to know or want to do about distillation and put them in sort of a block, right? So it's a unit operation in chemical processing, for example. Heat exchanger is a unit operation, if you will, right? So that's another unit operation. Chemical reactor is a unit operation. By that I mean that everything you need to know about a chemical reaction, the vessel and any catalyst and so forth, you're going to sort of put them in a box and call it, something that describes that particular operation. In this case, a chemical reactor, whether it is a reactor like that on the left or a catalyst reactor like that. It's a unit operation. So why do we need to have unit operations? Because if you take a look at a process is sort of very complicated, right? It has a column here. It has different kind of boxes that do different things. You could have something that exchanges heat, something that converts one chemical into another chemical, does some separation and so forth. So the unit operation concept is a way to understand a chemical plant in units. What are the different units and how are they sort of assembled together? So why unit operation? It helps us to analyze the chemical process a little easily. So to understand a complex process through individual units, in this case, unit operation. And the other advantage is that if you want to build a chemical plant, you don't build the chemical plant all at once. You build individual units and then you kind of join them together. So you can join up a distillation column, you may have a heat exchanger, you may have a reactor and so forth. So that's the whole idea. So we can assemble and then we can simulate them and then figure out if in fact when you put the parts together, how does the whole behave? So that's the idea. So you can do what's called process, can create a process flow diagram, do mass and energy balance, and size the equipment, find out the cost, so on and so forth. The other reason for doing these, starting these unit operations is develop a model. We're trying to figure out how will the plant behave when you assemble all these different operations into one, for example, and to be able to predict what will happen if one of your operation fails or doesn't perform as you designed it. What could happen to the rest of the plant. So by able to isolate, we might be able to isolate the performance or misbehavior of some particular unit on the plant, for example. And what you'll hear from Jonathan in a few minutes is he's actually going to describe an experiment in heat transfer. If you have models for everything, why bother doing experiments? And it turns out, for example, that very often a model tends to be an approximation of the reality. So we need to have some experiments to relate them to reality and ask the question, for example, do we need to change our models or perhaps we collected data incorrectly, something like that. So we need experiments so that we can improve our models, we can understand performance of a given unit, for example, and so forth. So that's the reason we do it. And then what he's going to talk about is a heat exchanger experiment where things are flowing countercurrently in opposite directions. You're going to see a situation like this, where there's a hot liquid and a cold liquid. The heat is being transferred from hot to cold. You'll talk about the experiment, and I think we're going to have a little video shot in the lab where you can actually see the students actually explain to you what they actually did. And in Jonathan's presentation, he will sort of give you the final result. He'll give you the essentially a project description, a project report about the different experiments. And you'll see lots of equations, stuff. Keep the following thing in mind. Essentially what it will show you is that you got to account for heat loss and you got to account for the heat gain. Are they equal? Are they not equal? How different are they? And so forth. And then you'll see different terms like heat capacity, and you'll see things like temperature change, and so forth. And again, the important thing is that we want you to look at it at these different equations and try to understand what the overall purpose is. Can you account for the heat loss and heat gain and so forth? And you'll see things like heat capacity, you'll see something like delta T, temperature changes and so forth. And again, there may be some terms you may not understand, but at least appreciate, for example, this is the actual experiment run by our students in the senior year in one of the classes, and then hopefully you'll be able to get a sense of why they did these experiments. And then you'll also hear about something called heat transfer coefficient, and then he will show you, what is the relationship between experimentally determined heat transfer coefficient and what the theory says. So they try to connect what they learn in the lab to what they may have heard about in the classroom and modeling and so forth. Okay, so you'll have a lot of fun listening to the video.